So I went and rearranged my room again, and the window is right behind me, and we got some blinding lights coming here. With all these blinding lights, you probably can't sleep until you feel my touch. Alright, I'm gonna see what I can do about the light. Also, this isn't even the right video title card. I'm gonna fix that too. That looks better. Also, there's a rotten banana peel on my desk, so I think I'll dispose of that too. We are in chapter 3. We got new concepts coming up, coming in fast, coming to you. And I'm gonna switch from my normal lined paper slides to grid paper slides. So big changes are coming. So this chapter is linear equations with two variables. So previously, there's a lot of words here. So linear just means lines. That doesn't make much sense now, but it'll make sense later on once you learn more. Equations, that's just what we've been doing, where we have something equal to something else. Equate as in equals. Equations, it's whatever, whenever we have a math sentence with an equal sign involved. And two variables. So instead of our normal one variable, solve for the variable by getting the variable by itself, now we're going to be dealing with equations that have two variables in them, and we'll see how to deal with that. We saw a little bit of that in the previous chapter and the chapter before that, where we had like I equals PRT, and we had to get one of the other variables by itself by moving stuff around. So this shows the application of having more than one variable, or it shows another application of having more than one variable. So we have something here on this slide, but I actually want to start you off with a refresher of a number line. We all remember a number line where, let's say we have 3, will be right here. And if we wanted to go to -1, be over here, and if we wanted to know the difference, we would just count 1, 2, 3, 4. If you wanted to put a dot at -4, you would just put a dot at -4. It's a number line. It's a line. It's linear. Okay. So just a straight line. It's just as if you were like walking down the street or driving down a straight road. If you started somewhere and you went east a few miles, if you went east 3 miles, you would be 3 miles from your start. So number lines have a few different applications, but the point is it's only measuring in one direction. Either we're going negative or positive. That sounds like two things, but it's one dimension. Like when we're measuring with the ruler, we're measuring a distance, we're measuring a length, it's one dimension. But now going forward, we're going to be using a lot of what is called a plane. A plane is a two-dimensional surface. So just like how the number line measured a distance, this plane we see measures a distance this way and a distance this way. So think of a sheet of paper or think of a map. It might be easier to think of a map for a lot of our examples. But now we're measuring in two directions. So that's one big difference. We call that a plane. And instead of just saying, oh, we want to go to 3, we need to know we're going to 3, and we also need to know which direction we're going this way. So like think of a map. If we have a house that's right here, we have a little house. If we just say, oh, it's at 2, that doesn't help us because there's all these other places. We're at 2. It's at 2 in this direction, and it's at 3 in this direction. So kind of showing that it's not enough if we have two dimensions, we got to have two different pieces of information, just like any other map. So 2 dimensions, 2 pieces of information, 2 variables. So what I just said was I said the house was at 2 in this direction and 3 in this direction. If we wanted to make a point on the map for that, we could say the house is at 2, 3. Meaning it goes 2 in this direction, 3 in that direction, 2, 3. Whenever we're trying to place things on the map here on this Cartesian plane, we start with our horizontal axis, also known as our x-axis, and then we count our vertical axis, also known as our y-axis. So that's why we call this 2, 3. If I wanted to put a school over here, where would that be at? Well, how many is it in the x-axis? 1, 2, 3, 4, 5. Okay, so we know that our first part of the map is a 5, and then if we look on our y-axis, follow that line back, it's at the 1. So we would write this as 5, 1. These ways of mapping things are called ordered pairs. Pairs because there's two of them, ordered because it goes x-axis then y-axis. So let's review some of the definitions so far, and then we'll go over a couple more. So any two-dimensional surface is called a plane, because we have one dimension, two dimension. We call this a Cartesian plane because I thought it was somebody's name. It might not be. Another way of calling this is a rectangular coordinate system. These destination markers are called ordered pairs, and they're also called, what did I just say? Coordinates. So y'all are already familiar with the word coordinate, so it's kind of like that. We just have different names for it. So I'll go ahead and write all these down, and it will be in your notes too, so write it down on your piece of paper. Okay, give you a second to look at all these, and you can copy them into your notes. All right, and so just review all these terms as you write them down. And remember for these, the first number is going to be whichever value is on our x-axis or our horizontal axis. Oh, I wrote it wrong. This should be oh wait, no, the house is right here. Yeah, 2. And then the second number is going to be our y-axis, so 3, 3. And we can remember this. We crawl before we walk. So we remember we have to go crawl across the ground before we go up and down and stand upright. And that's how we remember which one goes first. One final thing, see how the plane is kind of broken up into 4 parts. If we follow the lines, we got one part here, one part here, one part here, and one part here. We call these quadrants. Quad as in 4 quadrants. So we call this one the first one. We call this one the second one. We usually use Roman numerals to denote it. This is the third one, and this is the fourth one. And you might say, oh, that's a little out of order. Well, it goes counterclockwise. So we start in this one, we go to this one, we go to this one. 1, 2, 3, 4. We won't use much of that yet, I don't think, but just keep it in mind for later. Okay, let's go ahead and go through some of our examples. Page 93, example 3.1a. It gives us a few points that it wants us to graph. So first one is 3, 2. So we go 3 over, and we look at our x-axis, we find our 3. We go to our y-axis, we find our 2 right here. And so we find where these two guys meet, which is right here. Next one, we got -3, 4. So we can also go in the negative direction for these planes. Don't get confused by that. Also, I missed a little. -3, we find -3 on our x-axis. Right here, we find +4 on our y-axis. Right here, we find where they meet. Boop, boop, right here. All right, -4, -3, we find -4 right here. -3, it's over here. We find where they meet right here. And then we got 1, -2. We find 1 right here. We find -2 right here. We find where they meet right here. And I'll go ahead and write the coordinates so you can see that next to the dots. I just realized I made the mistake. I put this on -4, -2. The book said -4, -3. If you caught it, congratulations, you get a point. Okay, so if we notice something interesting, see how that we have 1 in each quadrant. This is in the first, this is in the second, third, fourth. The dot in the first quadrant, both numbers are positive, positive, positive. And the dot in the third quadrant, both are negative, negative, negative. And then in the second, we got a negative and a positive, and in the fourth, we got a positive and the negative. That's true of any dot in one of these quadrants. So any dot put in the first quadrant, both will always be positive. Any dot in the third quadrant, both will always be negative, and then same rule, whatever the rule is, applies to the other two. We'll go more into what that means later, but just now notice that that's a cool thing. Let's take a look at how ordered pairs, remember these guys, relate to equations. Remember a math sentence with an equal sign. So what do we notice about this equation? Well, we got 2 variables. Remember what we said in a previous lesson? Whenever the variable is by itself, we call that the dependent variable because it's going to depend on the variable inside the equation. So independent, usually we're the ones changing that one. Dependent is a result of whatever happens to that first variable. It doesn't apply in the example we're about to do, but just reminding you of some vocabulary of dependent and independent. Okay, so we have an equation, and it says determine if each point, each ordered pair, each point, because it's called a point because it represents a point on our graph. Determine if each point satisfies the equation. Satisfies means is the equation true? So remember that our first number represents our x-axis, so we can actually say that x is equal to 0 in this case, and 2 is a part of our y-axis, so y in this case, so we're going to do some substitution. So instead of writing y, we're going to write 2, and instead of writing x, we're going to write 0. We're just doing nothing fancy. We just know that our ordered pairs represent x and y values on our x and y axes, so therefore we can do some substitution here. So let's simplify. Can we do anything to the left? No, that just stays a 2. On the right, we got -3 times 0 equals 0. Rewrite everything else, and then we got 2 equals 2. Is that a true statement? Yes. Therefore, that point satisfies our equation. Let's try the next one. Let's substitute 3 for x, -7 for y. So we'll rewrite it. -7 equals -3 times 3 plus 2. Can't do anything to the left, so just rewrite it. On the right, we got -3 times 3. 3 times 3 is 9, and that negative makes it -9. Rewrite the plus 2. -9 plus 2 gives us -7. Is -7 equal to -7? Yes. Therefore, that point makes our statement true as well. And let's do the last one. Instead of writing y, we'll write -4. And instead of writing x, we will write 1. -4, -3 times 1 is just itself, -3. And then -3 plus 2 gives us -1. Is -1 equal to -4? No, therefore this does not satisfy the equation. So just goes to show you that some points will satisfy an equation and some will not. But also notice that we had two different points that made the statement true. That's a little bit different from some of our previous problems, because with one variable, usually it was just one point to satisfy the equation. Now we got a couple that'll make it true. Okay, so let's remember a couple of the points we did from last time. We had a 0 and a 2. We had 3 and -7. Those were the ones that were true. And let's write a few others. Okay, so let's go and graph all these points. So 0, 2, we find the 0. The 0's right here. We find the, and then we go 2 up, 2. Let's graph the next one, 3, -7. Find the 3, go down -7. It's off the page, but just pretend you know where it's at. -3, +11. That's also off the page, but in the other direction, so just pretend you know where that one's at. We got 1. Then down -1. So another way to think of these x and y's, if it's a positive x, we're going to the right. If it's a positive y, we're going up. If it's a negative x, we're going to the left. If it's a negative x, we're going down. So sometimes I'll say over this many, up this many, or left this many, down this many. It's just another way of thinking about how we're doing these things. So for this next one, and we're always starting at the middle when we say that over. So if I have the point 1, -1, first one tells us we're going +1, which means we're going right 1, and the -1 tells us we're going down -1 from there. And then when we're graphing the next point, we can start back from the middle again. The middle is called the origin. I forgot to put that on the first slide, but that's important to know. Oh, I was recording that. Crap. Oh well, you just got a few extra seconds added. Okay, and then this last one, we'll start at the origin again. The -1 tells us left 1, and the +5 says we're going up 5. So we'll go right here to the point -1, 5. So if you notice something about these points, and then remember we have imaginary points off the page, we can actually draw a line through these points. And I'm not going to draw it very well, but believe me, it's a straight line. And it actually will go, dang it. It'll actually go to the imaginary points. That's a crappy line. Let me try one more time. Nope. Nope. Better. Oh well. Oh wait, isn't there a line I can draw on this Jamboard? It doesn't matter. Anyway, just believe me, it's a straight line. So see, all these different points together, they drew a line. Remember, what was special about these 2 points? They both satisfied the equation. And by satisfied, we mean made the equation true of y equals -3x plus 2. And if we look, all these other points also actually make this statement true. And if we graph all these points, they all form a line together. That's kind of interesting. That's why we call this linear equations, because it's an equation, and when we graph out all the points, all the ordered pair combos that make it true, we get a line. That's what's special. And we have 2 variables. So now the title makes sense. Linear equations, equations that make lines with 2 variables. So yeah, and we can actually come up with points we didn't even write down yet. This one is probably -5, 3.5. Not a nice number, but it would make this statement true as well. So yeah, so now this, whenever we have start with an equation and then we find all the points that make true and graph it, we call that graphing the equation. But this is if we have the points already that we know make the statement true. Let's say we just start with something and we don't know, start with an equation and we don't know what points make it true yet. Let me show you how to figure that one out. So let's say we start with this equation, y equals 2x plus 1. We want to come up with some points so that we'll be able to graph them on a chart, but we don't know what points make it true. So it's real easy. We're going to make a table. So we have our table here, and we just want to start picking. Remember how I said this is dependent On our independent variable is the one we choose, and when I say choose, it applies to cases like this. So let's start with a number for x. Let's say we want to start with the number 1. So if we plug in 1 to the equation, let's try it out. 2, substitute the 1. We have 2 times 1, which is 2. Rewrite everything. And then we got 2 minus 1, y equals 1. Okay, so we can say that if x equals 1, y will equal 1. And if we were to plug these, the 1 here and the 1 here, from this table, we would see that our statement would be true again. Let's pick something else. Let's pick 2. If we do 2, we got 2 times 2 is 4, minus 1 is 3, which means our y would be 3. Okay, and if we plug that in, our statement would be true. Let's try 0. 2 times 0 is 0, minus 1 is negative 1. If x is 0, y is negative 1. And let's do one more. Negative 1, 2 times negative 1 is negative 2, minus 1 is negative 3. So if we got negative 1, we'll get negative 3. Okay, so we've just got a group of numbers here. But the thing is, these are the same as our ordered pairs. So 1, 1, 2, 3, 0, negative 1, and negative 1, negative 3. So if we were to graph these out, we would get a line, and I'll do that on the next slide. So see, we got our points, they're on the line, and once again, I'm going to butcher the line. Ah! Not good. Anyway, so if we could keep going with different values of x's forever and just make our line longer and longer. And our lines, as you see, they go off the page, and we can even draw arrows, and in fact, we're supposed to draw arrows. The arrows just tell us it keeps going and going and going. You can find as many ordered pairs that make the statement true as you want. Okay, there's more examples in this lesson, but I think that's a good start. Just fill out your lesson guides, and that should give you enough to know what's going on when we do the practice problems in the next video. All right, see you there. Bye.